remind you that there's pizza, beer, etc. Not necessarily in that order. The transcript later today. And okay, well, let's have our talk. Very happy to have Moira Chas from Stony Brook, and she'll talk about different theorems.
So I'm really delighted to be here. It's a bumpy arrival, but I'm happy to have made it. Sorry I missed the canoeing. I came for that, so it's very much. So what I'd like to talk about is like a long list of results. There's more questions than answers, and they're all of them inspired by my interaction with my computer, and I have human collaborators too. But the main one is here. So I'm going to give you the appetizer at the middle of the talk. I like Jean, but here this is a preview of the appetizer. That picture there has a meaning. Anybody can guess? No guesses? Nobody guesses? Somebody said a Chinese temple. The one in the left. But anyway, you have to stay with me and come up. It'll come at some point. Okay, so let's start with a torus with one boundary component, and let's do what we all know how to do. We're going to cut this torus with cuts that don't intersect itself or each other, from going from the boundary to the boundary, and you open up and you keep a memory of how you cut, so you want to reglue, and then we're going to look at a class of curves. Here I'm thinking free homotopy classes, but here I have a single curve, and then we look at the same curve in the surface, in the cut up torus. And what I'm interested in studying, and I'll be very interested from now on, is studying the self-intersection number of these curves. In particular, I want the smallest possible intersections numbers of the curve in the homotopy class, in the free homotopy class. Now, once we have the curve written like this, and this gives us a set of preferred generators of our surface, and the generator labeled by A will start somewhere here, go around, cross the edge labeled by A, enter at the same point, and come back, and same with the generator labeled by B. So this, again, this way of cutting picks a pair of generators. And when I pick a pair of generators, every free homotopy class gets a label. And in this case, the label of this class would be A, B, capital B, capital B. And I write capital B instead of B bar because the computer is much kinder, when you use capital B than when you use B bar. So this curve, I think I start here. You start somewhere here, go to A, enter here, do A again, come back in the edge labeled by A bar, A for the third time, then go here, do B, come back here, A, now you're here, B bar or capital B, B once more, and we're back where we started. That's the curve. And as I said, I'm interested in the self-intersection. In particular, I'm going ahead of myself. Now, these are free homotopy classes. There's no base point. So instead of thinking of a linear word, I'm going to think of a ring of letters. So this is in fact a better picture of the label of my class. It's a ring of letters. This is just this class, but I have to stick with permutation, and I look at this is the class I'm going to consider. Now, this is a super quick review, but you have free homotopy classes always. You have sufficiently nice space. There's a one-to-one corresponding with the conjugacy classes in the fundamental group. And if I have a surface with boundary, the fundamental group is free, so these are also reduced cyclic words in the generators in some set of minimal generators of the fundamental group and their inverses. So now let me look at the self-intersections. I'm going to study this particular one. Why is it there? I want the word that labels the class tell me why the self-intersection is there. So this self-intersection appears in the intersection of these two arcs, in light blue. Now, why I have this particular arc? Well, this particular is here because at some point let's see, I have to do it in the middle. I enter here, and I enter here because my word has a capital B. I came up here, and there's a second capital B that made me do this R. So every time I have a B, B together, I'm going to have an R from here to here. Same thing by this one. This is because I have a AA in my word. So this is regardless of how my word is, how the rest of the letters are. No matter if I have a million letters or just these six, every time I have an AA and a BB, I'm going to have two arcs like this, and these arcs are going to cross. So here this self-intersection, gets assigned a pair of subwords of my word, a pair of subwords of two letters. And in fact, you can generalize this, and I don't have time, so I will not. But this, here are each self-intersection gets a certain pairs of subwords of the word. This can be found totally combinatorial, and the main idea is you have to think of these two blue edges crossing. That's the idea. There are cases that are slightly more complicated than that, but it's just push that idea a little further. So these are the words, and this is a theorem. Berman series first gave this algorithm to determine when a word gave get a simple curve, has a simple representative, and then Cole-Lustig extended to count the self-intersections, and I gave you, I put my name there, small, but this is the same Cole-Lustig algorithm, but it has a slightly different form that I'm going to use later, so. So there it is. And these subwords, what determines these subwords? How? Because I can just put this algorithm in my computer, and my computer can compute self-intersections. Well, the information it needs is how, the generators intersect, and this is how. What is this word? In this case, it's A, B, capital A, capital B. So the way I glue the way I glue the surface, which is the way the generators intersect, will determine how all the words intersect.
Is there some assumption about cyclically reduced words or something?
Yes. Very much assumption. Yeah, all my words are reduced, and they're cyclically reduced. Yeah, first and last letter are not one the part of the other. Oh, okay. So I know this will happen. Let's see. Oh, this is just, I said, well, we have a surface with negative Euler characteristic, and look at the free homotopy class, and I want to assign to each free homotopy class occurs on a surface 3 numbers. One number is the one I discussed before, the smallest possible self-intersection of a member of the class. So here is 1, these are 2 representatives, this intersects twice, this 1, that this is the self-intersection under the class 1. Now, if your surface has a hyperbolic metric, a normal hyperbolic metric will also have geodesic boundary, then you also have the length of the shortest geodesic in that class. And we had this little miracle that the geodesic in that class realizes the minimal self-intersection. And finally, if we have also a chosen favorite set of generators of the fundamental group, then we can write our class, well, as a word, but in particular, the shortest word will be the word length of that free homotopy class. Yes?
Does a triple point count as 2 intersections and 1 is...
Good, thank you. I hired you to ask that question. No, it counts at 3. So because I intersect pairs of branches. So triple, we move it a little bit, and this is 3. Thank you. Okay, so this is what I want to do. I want to study relations and statistics and structure of these 3 numbers all together. And I think I put a very ambitious abstract and a light. I said I would talk about the Goldman Lie algebra, but I doubt I'd have time because I added stuff that I didn't was planning in the moment I wrote the abstract. So let's start counting. I mean, this is going to be a review. Let's see if you learned the talk of Genia that was here before. Maybe I should ask you to give me the talk. So the first counting is that you want to count all geodesics in a surface up to length, geometric length L, and we know that this is E to the HL divided by HL, where this H is the entropy of the geodesic flow. And then we have this beautiful result of Maria Mirzakhani that if you want to count only the geodesic we know self-intersection up to length L, well, that grows as a polynomial, and the degree of the polynomial is the dimension of the Teichmuller space of the surface, and she will compute the leading coefficient of that. The leading coefficient depends on the metric. And this is just a reminder that simple curves are not that simple. We saw it before in Eric's talk. So, and then Igor Krivin, using Mirzakhani's results, he also proved that all the curves of self-intersection 1 up to geometric length L, they also grow as a polynomial of the same degree. We don't know the coefficient, but we should do it. And of course, the natural conjecture, which I think Genia had some partial result, is, well, how do the classes with self-intersection K, here we say with self-intersection 0, how do the classes of self-intersection K grow? I have in yellow, I have my questions. So sorry, I try to put everything in yellow, hope I achieve it. And then, well, it's easy to do a little, combinatorial argument to show that if you count how many free homotopy classes of word length, I should have written equal to here, I realize. Although, well, this is exponential, probably doesn't matter, but this is 2n minus 1L divided by L, and you can see because, well, how do you construct a word, If you have one letter, you have 2 letters in total in your alphabet if you have n generators, but there's one forbidden because these words are reduced, so you have, and then it's a ring of letters, so you have to divide by L. This is a little overcounting, but, when L is large, it's pretty close. So again, we could ask, we have this geometric question, what is the growth of all the geodesic up to length L? I could ask, what is the growth of all free homotopy classes up to worth L, with assumption that the self-intersection is K. And the conjecture is the growth, well, is the same. Recall that there is a quasi-symmetry between these two worlds. So if we know the growth in one, the growth rate, it will be the same in the other one. The coefficients are now going to survive, and we should work and find them. Okay. So this is what I did with my MacBook Pro. So I did a table. So this table contains, in the, say, the row 2 and the column 1, you contain the number of cyclic reduced words, which are non-powered. This is the number of free homotopy classes expressed with a word of 2 letters and with self-intersection 1. So for instance, self-intersection 0 and 1 letter, well, they are the 4 generators. This is the torus with 1 boundary component. These are all, all the letters of the one, we know they are, self-intersection 0. Self-intersection 0 and 2 letters are this here. Self-intersection 0 and, 4 letters, for instance, this is the boundary, which, of course, you expect to find here, and so on. So this table, this algorithm to compute words is doable with a computer, but painful for humans. So I'm happy to have the computer, and I can, put it and compute more, and even more. And then one thing you can do is, once you have this table, you can try to test the conjecture about the growth. Now we want to study the growth of these columns. I mean, well, sum up to a certain, I want to sum up to a certain length of these columns. So this is a new table in which, in the cell, say 12, and column 0, I'm going to put how many words up to length 12 I have, which have self-intersection 0, and I divide this by 12 squared. Then my conjecture, in this case, the growth should be like a quadratic polynomial. So I'm going to add them all up, that you saw in my column, and divide it by, the word length squared. And if this conjecture that this is, converges to a certain number times L squared, well, I should have seen these columns that you can see because we have this beautiful screen. This seems to converge to something, so we have to, well, this should be yellow because this is just a computer result. This thing seems to converge. We have to find a way to find these numbers and prove that indeed converges. So this, this is really supporting this conjecture then. And then here, this is the length 20. The length 20 takes days in the computer, days in the, like, I don't know, maybe a week or so to compute. So, did I do it? Oh, I was just showing how the convergence, here this is intersection 0, these are the coefficients. This one seems to converge quite quickly. Of course, length 20 is nothing, but still is suggestive. This is self-intersection 1 and 2. And these are the coefficients. So for each k, self-intersection k, remember that the growth is a constant depending on k times L squared. The coefficient seems to grow exponentially, which of course, we have to expect because I said, well, we have e power L curves. So if I have to add L squared many times and I have to get e power L, I better get big coefficients. Okay, so this is the table now for the pair of pants. Now what's the difference between this table and the other table? Essential difference. There's fewer simple closed curves. Anything else? There's zeros on both sides. I mean, there's finally many. So here, we have this, and you never got it. Once you start to get numbers before, there's never a zero. Here there's zeros, and here there's zeros.
Actually, those are not conjectures.
Those are, I can prove it. That's a challenge. This is super. No, we know that we know there's finally many curves of self-intersection I for each I in the pair of pants. And there's many ways of proving this, but one nice way to see it is, well, we know by an easy argument with the Euler characteristic that there are finally many simple curves. There's only 3. So now take a curve with self-intersection and go to a self-intersection. Self-intersection divides it in 2 loops. You can put it. Now let's do what's the word? Complete induction. So you can put finally many here and finally many here. There's finally many in total. And notice that I could do that argument for every surface. So what am I proving? That every surface has finally many? No, because in this case I have the 0 step in the induction that allows me to do that. So crucial step that finally many simple curves. And well, this is just something I like to know. This is the number of curves of self-intersection I as a function of I in the pair of pants. So the 3 with 3 figure 8, that with self-intersection 2, and so on. And if somebody can go out and come back with some way of producing the sequence, I'll be really thankful. Yes?
Have you plugged it into the
I did. And nothing comes. And somebody asked, is this a theorem? Well, this is kind of a theorem. I mean, well, you have to trust, my programming. But in fact, I can compute a few, and then I guessed, I think the last 5 or 6, and I'll show you how did I guess. And I don't really know how did I guess. I mean, I don't really know why it works, but this is how I guessed. So this is the table for the pair of pants. Again, remember that in the rows I have word length, and in the columns I have self-intersection. Now here, to make life easier, I divide by 2. Since a curve and a curve, with the opposite orientation, I'm always going to have it, and they're always different, I divide everything by 2. So I have here 2 words of self-intersection 0 and 1 letter, which are the 2 generators, and so on. But when you produce a table, I painted in colors the numbers that are the same. As you see here, I have a 2, then I move this L, like a chest L, and I have a 2, and then I move this chest L, and I have a 2, and 2, and 2, and 2, and so on. And then there's a 6, and once this 6 appears, it shows up all the time, and then there's a 20, and then 32, and then 2, 6, 12, 20, 32, 52, 92, 23, 6. As much as I can compute, these numbers keep repeating. And yes, I put it again in the encyclopedia of integer sequences, and nothing came out. I tried with Mathematica to find the function, to find generative function. No idea. Those are, but they are there. If you look at the words, the actual words producing the self-intersection, from these ones I can get the next, because it's just adding a little something. These ones are, for instance, AA, AB, AB, and BB, AB, AB. So, no, I see it wrong. There's 2 A's and then C. So this one of the 3 are AAB and BBA. And then you add an AB and then you add an AB, and that's how you get these 2. And there's similar patterns, but it still doesn't explain why this repeat.
What's the difference between the cells that are in white and the cells that are colored?
Oh, I color the ones that have the pattern that
I see.
repeats.
Okay, so there's no obvious pattern in the white cells.
No, but if anybody sees this is, this could be joint work, this stuff.
So I see. So when you had the conjecture a few slides back about the rate of quadratic growth,
Yes.
So it looked like the convergence there was very fast. Somehow here it looks like the convergence is after 2
Well,
seconds.
here the rate, this is a constant. Here of pants is a constant. The dimension here.
Right. Sorry, but there's sort of a this skew stabilization or whatever. The fact that you're sort of stabilizing along these diagonals is happening. Right, happens fairly quickly.
Yeah, but then you're 0 forever, so the rate of growth is 0,
Right.
like a constant. I don't know if I understand what you're saying.
So in the previous conjecture, is there a version where you conjecture how fast it'll converge, the rate of quadratic growth?
No. It's quadratic or no. Here is not. It's a constant. Yeah. Anyway, so here there's lots of yellow because this is open. Oh, and then, well, when you have a pair of pants, I pick 2 generators. These are 2 boundary components. But why do I pick 2? There are 3, and there are 3 equally nice in their own right. So the third boundary component complained, and I had to make a table where the 3 of them are treated, equally. So now let's make the same table, but add the relation. You have the generators ABC, and you put ABC equal to 1, and this is it. And again, it's colored, not because I like colors. Today I'm pretty strict in general. I like color, but this is colored because also there is some point. So the point is that when you look at this diagonal, this one grows like this polynomial in degree 2. When you look at the next diagonal, starting at this cell marked here with a darker square, it grows at this polynomial. So this is the term 1, 6. When you plug in 1, and then you plug 2, and you should get 18, and so on. And the third one grows, and the fourth one grows, and all of them seem to grow like a polynomial. So here is some hope that I have maybe to find, an explanation or prediction for my favorite sequence. Any question?
What about with the torus if you do 3 derivatives?
Well, I don't know. But the torus has natural 2 generators, and every basis is the same. In some sense, you have many bases, but they're all the same. The pair of pants, in fact, it's a little weird because I could use as basis, I could use any pair of elements that are bases in the torus that give you simple curves. You can look at it in the pair of pants and use it, but has no geometric meaning. But on the other hand, using simple curves as generators is meaningful.
So what's the formula for which polynomials you're going to get?
I don't know. I just computed,
I see.
mathematically computed, yes. Well, I can compute it, but first I was just trying to find a function. I didn't know what was falling on it. This is, the last weeks, we were grading with Tony Phillips and, finding these, in
So
parallel.
you think they're all quadratic?
Yes. I mean, it's as much as I can, I have a piece more of the table, everything I can compute, which is up to 12 or 13 letters.
Do you think that they all have non-zero constant term? And the only difference
They all
is
have
like,
they all have positive, except for the first one. They all have non-zero constant term. They all have positive coefficients, and that's it.
is there any pattern to like which ones have all three terms and which ones just have two? Or
The ones I found, only these two have two, and all the rest have three,
how many do you
and they
find?
grow pretty fast.
How many? Did you just find these four or is there more?
I think I have about 10.
Okay.
Yeah, and the coefficients are bigger. The leading coefficient in particular. Well, in this case, it's 30-30, but then all grow. Also. Okay, moving on. Now let's do statistics. So we have 174. I'm not going to copy read the number. I won't be able to. Millions of classes of word length, and I'm going to look at this in the punctuators. It's a word length of 20 letters. So if you pick one at random, what is the probability that the self-intersection is 42? Anybody knows? Ah. Okay, well, we can compute it, okay? I have this table, I computed up to 20, so you look at how many you have, and then you look at the total, and you made a portion, and you get 0.03 something. So that's the probability. Now, just indulge me to do this. Suppose now we look at a Gaussian distribution, and suppose that the mean is 20 squared divided by 9, something about here, and the standard deviation, the standard deviation is 9.94, etc., etc. And I'm going to compute the area under the curve between 41.5 and 42.5. And it's so close. Is this a miracle? Beautiful coincidence? Yes.
Did you just fit the numbers to the Gaussian? Like where does 20 and 9 and so forth come from?
You know. Be patient. 20 is because it's length 20.
Oh.
The 9 is a constant that is the same 9. It could be different, but I'll tell you now. So this is not a coincidence. There's very few coincidences. And let me go back to tell you, the theorem behind this. So let's look at the table now. This is again the table of the free homotopy class of the curves in the totals with one boundary component. And this is the row A. So these are all the words of 8 letters, and they're organized by the self-intersection. We have, for instance, 16 simple words, or words labeled in a simple curve. And let's put a rectangle over each square with a height proportional to the number of curves you have there. So here it is. You see the shape. Now let's do the same with the 20. There it is. So I was just playing with the computer when I found this, and then I wrote to Steve Lally, who's a statistician at the University of Chicago, and I said he worked in similar problems, mostly in the geometric side. He was computing, I mentioned his result a little later, but I said, I think this distribution, the self-intersection sampling by word length seems to be a Gaussian. And he answered, well, I don't think so. So I sent him an email with this picture only. And he said, let's prove it. And later on he said, no, he works with Gaussians, but this is the Gaussianest, thing that came from his brain. So this is the theorem. So we have a surface with boundary and negative Euler characteristic, and we have two constants that depend on the Euler characteristic. You'll notice that this constant, when I plug in -1, here I should get 9, and here I'm going to get 1 divided by 18. So then, when L is large, this is saying that if I appropriately normalize this distribution, you know, when L is very large, this gets closer and closer to a Gaussian. Okay, and recently, a student I have jointly with Dennis Sullivan proved an analogous result for closed surfaces. So, just a cute fact about this. So here is the theorem again, rephrased. And now suppose you have a circle, and you want to throw sticks on that circle, a number of sticks, and you want to count the number of crossings. But you want to throw them so that, you know, the way to throw them randomly is pick 2 points at random in the circle with uniform distribution. So, what is the expected value of crossings? Well, if you go to a probability book, it turns out that it's n squared divided by 6, where n squared is, you know, the number of sticks. Now notice that, you know, when my Euler characteristic is huge, this is close to 1/6. And the mean is 1/6 times L squared, and 1/6 are the number of sticks. So 0.6. So this is pretty good. But the variance of the same thing is n q divided by 45, which is the same thing I have here, you know, when the Euler characteristic. So for me, I jumped up and down and said, I found it after the paper was published. So it was so nice to have these two 45s there. Okay, so let's see. When did I start? How much do I have? Okay, I just say very quickly something about the proof. And I'm not going to, you know, go into the dirty details, but you know, we start, you know, we look at all the cyclic produced words, you know, and each one has the same measure, and we want to sample here. And then to study this, instead of this, we're going to open up, and we have a map from the open up words to this, which is almost always n to 1, you know, or yeah, n is the length, L to 1. You know, it's not L to 1 because I have some powers, but that they're not enough, not so much when L is large, so I can disregard them. And then we're going to look at this inside all the, you know, reduced words. And then we're going to put this one inside by projection. There's a projection from the reduced infinite words. And here, you know, is where, you know, one could do nice statistics. Now, if you remember, I start my talk by describing this algorithm of intersection, and I said, well, self-intersections are a one-to-one correspondent with pairs of subwords. So, bad luck for us, because if you suppose that by some other miracle, self-intersection where you want the word correspondent with single subwords, well, counting some words will be a process that will typically give you a Gaussian, you know, with ease, you know, like how many, you know, what is the distributions of the number of A's you have in words? That's a Gaussian. But counting pairs of things is a more painful thing, and you need a statistician to help you. And so we, you know, this uses something called U statistics, and it takes a little work. It's not horrible, but it's, you know, some work has to be done. So now, why do we have this mean and this variance? So this is a glance of the idea of why do we get this constant multiplying L squared for the mean and the variance. So my curve is made of pieces like this, and if my Euler characteristic is n, I'm going to have here, this is a 2n-gon, it's a 4n-gon, you know, because half edges are labeled and half edges are not labeled. You know, the labeled edges are the ones that I glue. But here I have k, you know, edges are labeled, and 2n minus k minus 2 edges that are not labeled. So let's count the pairs of length 2 of words, you know, the pairs of letters of, the pairs of subwords of 2 letters that are going to have a crossing with this one. Well, I have to go from here to here, from here to here, so I have 2k times n minus 2. So if I want to count the total number of crossings I have, well, I have to do this for all, you know, for all possible sticks here, and, you know, I put, you know, the beginning at each of this. So I get this sum, which is 16n squared and 4 divided by 3, so, long polynomial. And on the other hand, the total number of, 2 letters or words is this one, so the proportion, if I portion this divided by this, is 1/3. So that's the type of ideas that will get me that constant. You have to do a, the finer analysis, but this is the main point. Okay, now, so here is the question. So let me review what I did. I took all the words of a certain number of letters, each one has a self-intersection, and study the distribution determined by self-intersection. But now what I can do is, instead of this is sampling by word length, I could sample by geometric length. And what happens then? Well, no theorem. I don't have any theorem, but here is an experiment. So this is an experiment I did with, some parameterization that the king of matrices, Bernie Maskett is the king of matrices. You need matrices, 2 by 2 matrices to do something, and he has them in his pocket. So here, using a certain pair of counts, in this case is, they have boundary components, each 2, 2, 2, but I did many, many, many examples, and they all work the same. So I count how many simple pairs up to length 30. There's 2, how many substances component to length 30, and so on. And this is the histogram corresponding to this. So now, I wrote again to Steve Lally and I said, I think this distribution is a Gaussian. And he said he thinks it's not. I didn't think I should send him his graph. I didn't do it yet. Although, I think he's thinking of closed surfaces. And I don't have a way to experiment with closed surfaces yet. Closed surfaces has 2 problems. First, there's no this neat way of listing words. The free homotopy classes are just a list of words. And, it's another one that I may talk a little later. So, we don't know yet. I'm going to skip this. Oh, the first thing he said is that when we compute, one thing that happens is sometimes you experiment and you get this nice picture. But what happens if the variance, as the length goes to infinity, if the variance goes to 0, then you have to imagine your picture of the Gaussian is going to get thinner and taller, and it will be like, at the end, it's like a Dirac measure. So maybe, it doesn't convert to a Gaussian because the variance goes to infinity. Now, this is the picture of the variance divided by L cubed, because I think that the variance is a constant times L cubed. And you see, this is small, that doesn't seem to be going to 0. Of course, again, length 30 is nothing to, be so happy about, but still it's suggestive that, these 2 things don't go to 0, and I think, there's work to do, more reasons to leave. So, I like to compare, the reason I wrote to Steve Lally is because he proved this following theorem. He proved that if you have a closed surface, and then you look at all the closed geodesics up to length L, each one has a self-intersection, and you take the mean of those self-intersections, well, what you get is, when L is large, is L squared divided by, this constant, pi squared times the Euler characteristic of the surface. And he also proved something that is neat, that the self-intersection points are equally distributed in the surface. And let me compare with our result, if we, that the mean is, this constant times L squared. And you see there's a big discrepancy when the Euler characteristic goes to infinity. This here, the mean goes to 0. If you fix the length, the mean goes to 0. While here the mean goes to a square divided by 6. And why does this happen? Well, if you fix the length, but the Euler characteristic grows, the area grows of the surface. So you want to put a curve of length L in a huge, growing and growing and growing area. You have lots of space to not self-intersect. While in this combinatorial case, you are throwing sticks, when the Euler characteristic is huge, you're just throwing sticks in a circle, but they're typically going to intersect a lot. Okay, so we did another experiment, with Kara Lee, who was an undergraduate at that time, and again, Bernie Maskett. And now we are going to fix the metric again in the pair of hands, geodesic boundary, and you pick randomly 100,000 words with, they're reduced words, with 100 letters each. And compute the length of each of those words. So that gives you certain histogram, and I did it for these 4 different pair of hands. So this one, one boundary is 1, the other is 1, and the third one is 1, 2. In this one is 0.1, 1, 1. This one is 1, 10, 0.1. And the last one here is 0.1, 1, and 10. So anybody has a problem with my histograms? Not going to fight, just talk. Nothing weird, suspicious.
One of them certainly looks different than the others.
Yes, should. I mean, the only thing is, this looks different, but notice that here is 110, 0.1, and here is 0.1, 110. This is the same pair of hands, it's just the different order of the boundary components. Am I lying to you? I hope not, but who knows? Now, what happens here is that, the 3 boundary components, and the pair of hands, they are the same, but when I pick 2 generators, things change. So I'm sampling by word length, and then I'm giving the third component, the one that is not generator, a different tone. Now what happens here is this, when I go, the boundary says C, the one that is not generator, it has length 10. And at certain intervals it's going to go a few times around that boundary, and then since it's so larger compared to the other 2, that's the one that dominates the length. But if you take the experiment and do a little more, longer and longer words, these peaks, tend to get less steep. First it does like this, but then it's going to do like this, because you are rescaling. So at some point, when here I'm going from, say, the length from here is 300 to 450, but when the length is, the word length is much longer, the geometric length will be much longer, so these peaks are not going to be visible. So the conjecture is, this is a Gaussian. And there's a few ideas to prove it, but, so little time. Now here is my little appetizer. This is just a little intermission because it's a picture. So this picture here, you should look at it like starting here and then continuing here. So now, in a certain row, in the row, say, let's put here, this is the row, say, 7, and the column 0, is painted in blue if there is a geodesic with self-intersection 0, and the geometric length is between 7 and 8. So the row gives me the geometric length, the column gives me the self-intersection. And this is in a certain special torus with geodesic boundary. Now, the problem that I have when I experiment with this is, it's very easy to take all the words up to a certain length, which is less than this 1,000 algorithms. But how do you make sure that you consider all the geodesics up to a certain length? So when you have a pair of hands, the pair of hands has a nice decomposition. So this is the pair of hands. And we can pretend this is an octagon. with right angles, and this is the length of the component, of the boundary component A, this is the length of the boundary component B, and this is the length of the other one, and the other one. So now, notice that if I have, my curve is made by arcs like this, or like this, and so on. So this particular arc, going from A to B, is longer than this one here, because this is this is a quadrilateral with two right angles here. So then, and there's a similar bound for this one. So we're going to have that as a constant. This each if I have a certain geodesic G, the length, the geometric length, is going to be L1 plus L2 plus Ln, where the length of each of the arcs making the geodesic arc, Li is the length of each of the arcs making the geodesic in this decomposition. Now this one, as I said, each of these is larger than a certain constant that depends on the length of the three boundary components times n. But n is the number of arcs, and the number of arcs is the number of letters. So this is the word length. So this is C times the word length of G. Now this tells me that all the geodesics up to geometric length, big L, this is included, not smaller included, where I think is, let's see, it's all the geodesics up to word length L divided by C. Yeah, because if this one is smaller than L, then the double length is smaller than C. Then this I can look at, because I can list all of them. I mean, if the L divided by C is a decent number, my computer can go through them. And then from those, I'll pick the ones that are up to length L, and then I'm sure I'll consider them all. In the torus, I don't have a system to do it for any metric. There's many parameterizations to get all possible metrics. I could do it, working again with Berry basket for this particular torus, which has, is made of these pentagons that are they're right angle pentagons, and they have the length is, so if, this length and this length will determine my torus, because I just, these two edges that are perpendicular, and then take a perpendicular, take a perpendicular, take a perpendicular, and this one is the perpendicular on the perpendiculars, and you work out the numbers so the blue and the green don't intersect, and you're done. So then, using this, I did the length of the boundary component is determined by these 10 and 20, and it's 57.23 approximately. And so this is what you get when you do that table. So this is a nice structure. I mean, there are all these clumps of geodesics that happen that I think I'd like to describe and understand. I mean, I think, no, I'm super sure that I like. And of course, this is the one I showed before. They're organized at intervals of length 1, but 1 is, these are real numbers. So I prefer the 1, so I can do size 2, and this is size 4, and this is size 8. This one looks very much like the combinatorial by word length, when you squeeze things. This thing here, well, it's quadratic. We know that the growth here has to be the maximals of intersection is quadratic with a length. Anyway, another project for the future. Okay, so now, my last 10 minutes, I'd like to talk about some old theorem that I have, the partial result, which is very new. I think I even wrote it. So remember that there is a number with a property that any geodesic shorter than that number is simple. And this is the shortest, figure 8 ever. And just for fun, I computed it here. So if you have a pair of pants with one boundary component has length 8, the other one, 10, the other one has length 10, and the other one 50, the length of the shortest non-simple geodesic is 50.0006. And when you make the, the boundary components smaller and smaller, you see how this gets smaller and smaller. And, up to 0.001, the three of them, you already get the approximation I have for this. So that's the shortest figure 8. And we can think, like a generalization of these problems. So suppose you have defined a sequence. This is a sequence of real numbers. So for each k, consider all the geodesics of k self-intersection. Take the shortest one of those. That gives you a number. So what do we know about this sequence? Well, we know very little. In particular, naturally, it should be increasing, because you need length to have more and more and more self-intersections. Okay? So we know that the 0 is shorter than all the rest of the terms. And we know that S1, this is not that hard to prove. S1 is also shorter than all the rest of the terms. And here is an experiment, and I think right here. It is an experiment with a pair of cans, 3, 3, 3. The three boundary components, each of them has length 3. And here you have the length of the shortest geodesic of self-intersection 0. Well, of course, it's 3. The objective geodesic of self-intersection 1 in this pair of cans is 6.5, and so on. So this looks pretty increasing, as much as I can compute. This is a graph of the length as a function of the self-intersection, the shortest length as a function of the self-intersection. And, well, this is the problem I already described. Now here is computation that, made me, let's do this and then I'll do the next one. That made me suffer. I made the same computation in the torus with one boundary component. That same torus I described before. Here you have the shortest geodesic, and here you have the word, the corresponding word that realizes that shortest length. Well, if you look at here, 5 and 6, oh gosh, they are the same. When you compute the difference in whatever spreadsheet you are using with this program, my original program is in Java, I compute the difference is negative. So the one that I wanted, the 5, sorry, the 6 minus the 5, it gives minus 0.000 something. Awful. So then I look at the traces, and because the length is the course of the length is traced with some constant. So look at the traces here. Well, this trace is large. The trace in 5 is after. Okay, this is it. No. 5, 5.
3, 4, 5, 7, 6.
Yeah.
So this one is larger. Okay, I picked the wrong example because in the first one I did, the first time I had the traces were also, this is a lot of round-off error, but the traces are also given badly. But if you look at this in Mathematica, what happens here is that this particular metric is made of matrices, and the metric they have e power lambda and e power minus lambda, or e power 20 and e power 20 minus 22. And these two things, e power, in fact, I think I put it here. Yeah, here it is. So this is the trace. X is the length of one of the generators, and y is the length of the other generator. So as you see, there's a term that is 8x for y and ax for y. This is for the 5 and this is for the 6. And of course, this kills everybody, but these are very big, so these two make these things very, very, very similar. But all these little terms matter, and in fact, when you make the difference of those, the difference is positive as I suppose it is. So it seems to be increasing. And feeling pressure to put in so many questions and so little answers for this conference and the previous conference I have a proof for the pair of pants that this sequence is increasing. So you are the second audience listening to this proof. So the pair of pants has something special, which is that suppose that this is a circle that I'm going to map to the pair of pants, I'm giving my curve. And let me mark, so suppose that this point and this point have the same image, and this point and this point also have the same image. I claim that I cannot have a picture like this in the torus. This cannot happen. No possible.
Torus or the
Pants. Pants. I said torus, but I wrote pants. Trust my pictures more than my words. So why this happens? So this says that, well, if suppose that the image of this point is here, and the pants can be made flat in the blackboard. So I go to this point, and then I go to the other point. So this says, say I start here, go to this point, go to the other point. I'm looking at the image of my curve in the pants. And then go again to this one, and then come back here. I can't make it here without genius. So in the pair of pants, I'm going to write, I don't have a picture like this. So then what happens is that if I mark, so this is again the circle, and I'm going to put chords joining the points that are going to have the same image. So it has to look something like this, because they cannot cross each other. But then I have to have an innermost. And when you have an innermost, this is in the pair of pants, it's going to look like something like this. Beautiful colors should be used. So this one you can just remove, and you will get a curve with one less of intersection, but clearly shorter. There's a little trick that one has to be because I might remove a little more than I want when I do this. But that can be taken care of. So yeah, I'm almost at the end. It can be taken care of, so don't worry. I do have it. So let's see. I think I'm almost done. Yeah, these are just all these numbers that they were. Okay, just to end. So this is the two tables together. Now they're a little less painted in different colors. This is the pair of pants here. Now you recognize it because you have the zeros here. The oranges are 0 now. So the zeros are orange now. And this is the torus with one boundary component. And again, another interesting feature of these tables is that, when you have if you look at a row, once you have a number that is non-zero, here, there's never a 0. But all positive numbers. No proof of that, just observation. And this is, if I want to look at the combinatorial sequence of, now if I look at all the curves of intersection I, and I look at what is the length of the shortest, the word length of the shortest one, that gives me a sequence of integers, is clearly not strictly increasing, but, that sequence is the height of each of these, columns of zeros here, from here to here. How many do I have? And clearly, the experiments show they are increasing. Okay, I'm done.